Hello everyone, David Ostrowski here. CSE or CIS 2534, priority queues and heaps. This is a continuation of our week 6, chapter 6 content. I'm just going to take a different look at it. So let's get started. Some of the motivations for priority queues are any number of problems. It's interesting to note that a first come queue is essentially a priority queue. You are prioritizing your jobs by order of arrival, right? So you can consider that a priority queue, though it's not the traditional application or classic implementation, right? So among prioritization problems might include, because in terms of priority you think of something being preempted in most cases, okay? And some scenarios that characterize that a little bit better would include print jobs, okay? That sometimes you may need to run a larger job, maybe it has a higher level of importance. And in that case, a job could be terminated, or perhaps it could be a job that's bigger, could be scheduled at a different time, and so on and so forth. Emergency room scheduling, okay. If someone has a very life-threatening issue, they would preempt in most cases someone, regardless of how long they've been waiting. They would be moved ahead in line. Another classic example might be preferred customers are going to be given priority, let's say at a hotel or a restaurant, or someone who's comped or something like that may be moved ahead in some type of priority. So when we look at this, we look at from the perspective of adding an element and getting to remove the element. This kind of motivates our abstract data types. And we're going to talk about it in terms of an ADT, right? We talk about heaps. Heaps are classic means of implementing priority queues, but we don't need to use heap. A heap is not necessarily a priority queue, and a priority queue doesn't have to be a heap. However, they are matched well together and typically presented in the same context, even though it's important to note, right, that they are not synonymous with each other, right? They are the heap will support the priority queue. I could implement a priority queue with a simple list data structure or an array linked list, any of these types of, even a hash if I really wanted to, right? So that's why we look at these problems in the perspective of an abstract data type. That allows us to have that flexibility among the implementation, right? So here when we look at priority queue, the definition here is that of a collection of ordered elements that provides fast access to a minimum or perhaps a maximum element. And these operations at high level, at an abstract level, would include adding it in order and a given item. Peek will return the minimum, or in most cases what you would refer to as the highest priority value. Remove would remove that identified value. And then we have these other operations that are going to test whether the queue is empty, if we want to clear it, what the size is, and the iterator, okay? And these are noted as the big O1. Unfilled array, so you could consider using an unfilled array to implement a priority queue, as I mentioned, right? Just not going to be that efficient, but we can consider that as something that could be leveraged to implement it if you so needed it to, okay? So add, you just store it in the next available index as you would typically in a list. Peek would loop over the elements to find that minimum element. Just keep on continually making that comparison. In similar nature, remove would loop over the elements as well to find the minimum and then perform the necessary shift. To remove it, and just move over the items as noted. So how efficient is it? The add is big O1. However, peek and remove are big O(n), because you have to loop over the array, and that's dependent on the size n of an array, right? So you could consider using a sorted array to implement a priority queue. Here, the add would store in proper index to maintain the sorted order. With peek, the minimum element is an index of 0, and remove, you would be shifting the element to remove min from the index 0. How efficient is the add in this case? The add in this case would be big O of n, peek, big O1, and remove big O of n, big O of n. Consider we could use a double linked list to implement a priority queue. If I use an add, it'd be stored at the end of a linked list. The peek would loop over elements to find the minimum element. Remove would loop over the elements to find the minimum, and then unlink to remove and make the necessary attachments. Here, in terms of efficiency, as we compared, even in the context of our small example, adding the 9, 23, 8, negative 3, 49, 12, and then just doing a simple removal, you're going to have a big O n, and another big O n for add, peek, remove, respectively. Reason is the peek and remove, as noted before, must loop over the linked list. If it's sorted, okay, you can consider using a sorted linked list to implement a priority queue. And here you could store it in the appropriate place to maintain that order. And in this case, again, you're going to have some overhead doing that add. So it's a trade-off, right? It's a trade-off. It's going to be dependent on the particular domain in your application. But the peek and the remove, respectively, is going to invert the performance, right? I'm going to end up with a big O n, and then order 1 and order 1 for, again, the add, peek, and remove operations. So again, it's a function of how much data you're going to have in the list and how frequently you're going to be doing that add operation, right? So consider that I could leverage a binary search tree. Okay, I could implement a binary search tree to implement a priority queue. Here the add would store it in the proper binary search tree left right ordered spot. Here the minimum element would be at the far left edge of the tree, and the remove would unlink that far left element and unlink it to remove, right? So here I do the appropriate adds, and you can see the structure here. I have 9 at the top, 8 and 23 underneath that, negative 3 under the 8, and 12 under the 23, and 49 on the other side. So we have a lot more. So this, where we're going with this, right, is you're demonstrating the utility and the efficiency of relying on binary type, tree type property, going back to order log n, and this is motivating for the heap implementation, right? So here the add would be big O log n, and the peek and remove would also be big O log n. One point to keep in mind is good theory, but the tree tends to become unbalanced to the right. Unbalanced binary tree, so if you summate these operations, you can have a unique shape, as you see here. So that tree is unbalanced, that is a height close to n rather than log n, and that brings the expected runtime of many operations. It's going to upset your overall performance evaluation, right? This sets us up for what we term as heap A heap is a complete binary tree with vertical ordering. So it's a complete tree, meaning every level is full except possibly the lowest level, which must be filled from left to right. So a node may not have any children until all possible siblings exist. The heap ordering, if P is less than or equal to X, for every element X within the parent P, the parent's values are always smaller than those of the children. This implies that the minimum heap is always the root. A min heap, the variation map heap, stores the largest element of the root reverses ordering. So is the heap a binary search tree? How are they related? So here we can do the comparison, right? What would be a min heap and what wouldn't? Okay. Here, the first example with 10 going to 2080, and then under the 20, I have a 30 and 15. That would not exist as a min heap. Let's see. And neither would the 10, 20, 80, the next tree over, 40, 60, 50, 85, 99, 100. And neither would the third example there. Okay, just double checking this. So the reasons for these not being the min heap, 15 to 20, 15 is not greater than 20. So that's the node that breaks it. I don't know why they put the red mark there. Between the middle is because you don't have the 700 is misplaced, right? That could be under the 40s you see down here. So you have to go left to right. Here you have the oddball, but everything else is, the placement is correct. For the third, on the top hand, I have 10 and 20 should be replaced, right? It should be switched because 10 and 20 is higher than 10. It should be 10 switched with 20. And for the last one here, I have 10, 80, and then 99. It should be let's see if I have 10 to 20, 40, 20 to 60. I should have the 99 here and the 80 is the left child because I can't have a single right child. So that is the distinction there. Just as you see here, I have this go to 80, and if I were to add the 99, the 99 would be in that place and the 80 would be the left child to that. Again, filling it out from top to bottom, left to right. So there we have. That gives you a flavor, okay, of what do we mean by, and the max heaps goes in a reverse fashion, right? So I have 10, 20 on the first level and 30 at the top, so that's a max heap. I have a 21, 10, 48, and a 14 below the 21 to the left. That's okay. Here, the 24 should be a there should be a left child instead of right child. In that case, I'd have to interchange the I would have to put let's say 80 at the top, and then I would have 24 going to the left, right, instead of the right. And then 7 to 3, 7 is less than 10, 3 is greater than, or 10 is greater than 7, it's greater than 3, and correspondingly, the 33 is also greater than 10, 17. 40 is greater than 30, so that would make that incorrect as a max heap. So again, it's running in reverse. It's interesting to note, right, that the left doesn't have to, it should be the greater, or not necessarily, right, because I have 20 and 28, so it doesn't have to necessarily be left-right, just the child-to-parent relationship has to be less than. Heap height and runtime. So we know the height of a complete tree is always log n, right? And we know that if we implement, we know this from the sorting algorithms that we originally looked at when we looked at some of the initial controls. If we implement a priority queue using a heap, we can also provide the following runtime guarantees: a big O log n, big O of 1 for add and peak respectively, and for the remove it would be O log n. If I add an element to the heap, where should it go? If I insert a new element, I have 15 as the new node under the add operation. So I put it under as the left child under 10. It'd be, whoops, I didn't go through the whole operation here today. Well, we can come back to that. Okay, so this is the process, right, that you're going to, oh, here they added, okay, so when it's added to a heap, it should be initially placed as the rightmost leaf, and that maintains that completeness property. However, the heap ordering becomes broken, so I have to make the necessary adjustments. So this is the default placement, and I believe we have the, yeah, so we have the same, so it would be down here below 60 is the placement of the new node, and then we're going to do the appropriate shifts and bump it up. So we're going to bubble up that node, so to restore the heap ordering, newly added element is shifted or bubbled up the tree until it reaches the proper place. And you can follow the terminology percolate up, okay, by swapping with the parents. And that begs the question, how many bubble ups are necessary? Well, I'm not going to bubble up to the top because it's a min heap. It's not going to be the lowest. It's not going to be the highest node, but it's going to be the second highest, just below the 10. So you see right here, make the necessary operations and move it up to switch it with 15, 20, and correspondingly with 60. So a good exercise is to draw the tree state of the min heap following with items, and this is what you should come up with after that exercise. And again, it's maintaining the appropriate properties. We have the completeness property that's supported there. Peak operation, the peak on a min heap would be trivial to perform because the heap properties of an element is always a root. And here we're looking at the big O1 runtime. Peek on the max heap would be big O as well, returning the max and not the minimum. The remove operation, when an element is removed from the heap, how do we alter the tree? So in this case, I would make the necessary adjustments. Now here the heap property is broken. I'm going to replace it by the rightmost leaf, okay, to support the down here. It's going to be inserted above, and then you're going to make the necessary shifts and percolate down. In this case, restore the heap operating. The improper root is shifted down, bubbled through the tree until it reaches the proper place. Here they ask you to show the state of the heap tree after the remove has been called 3 times, and which the elements are returned by the removal. Okay, so that's the last of the slide. So you can take a look at that, and I'll try to generate more content, and we'll address that in a little more detail. So thanks for listening, and I'll be generating more content on this. Okay, thanks again. Take care. See you on the next one. Right, bye.